So in this lecture, we have solved from question number 165 to question number 168. Okay, there will be 2 or 3 more lectures after which work energy power will be completed off. Okay, then we'll start with rotational motion and then we'll go to gravitation. Okay, so we'll follow with mechanics and then jump to gravitation. In this question, what happened is, see, this is Earth. Okay, and here a ball is falling down. Okay, initially it was at rest. Okay, it was dropped from here from height h. Okay, what would be the velocity of the ball as soon as it reached down? The velocity of the ball would be under root of 2gh. Okay, v naught is equals to under root of 2gh. This much is known. Okay, what the question out here is saying, suppose a observer, okay, the observer itself was traveling downward with velocity v naught. Okay, there is an observer that has a constant velocity v naught in downward direction. Okay, he faces no acceleration, only a constant velocity of v naught downward, where v naught is equals to under root of 2g. Show that the velocity of the ball when the ball collides with the earth will be under root of 2gh irrespective of this observer or irrespective of the velocity of this observer. Okay, that means show that the velocity of the ball is equals to under root of 2gh, doesn't matter whichever observer you're taking it from. Okay, so from this frame of reference, okay, initially means when the ball was out here and the earth was out here, what is the velocity of the earth as seen by this observer? V naught upward, because the observer itself is moving downward, no? And what was the initial velocity of the ball as seen by this observer? Okay, v naught upward, because out here also the ball was at rest, isn't it? So v naught. What is the separation between them? H. Okay. Okay. And now what happened? Finally, what is happening? Okay. Finally, the ball collided with the earth. So when the ball collided with the earth, okay, what was the velocity of the ball? The velocity of the ball was v naught downward, but the velocity of the ball as seen by this observer will be 0. Why? Because see, the ball itself has a velocity v naught downward, no, and the frame also has velocity v naught downward. So if we equivalent that means v naught downward minus of velocity of observer v naught upward. So the velocity of the ball as seen by this observer will be 0. Okay, what was the velocity of earth finally? The velocity of earth finally would be v naught, because even finally the ball was at rest, no, sorry, the earth was at rest. When the ball collided with the earth, even finally the earth was also at rest, no? So the velocity of earth would be v naught. Okay, so can I apply work energy theorem from this observer? Final kinetic energy of the system minus initial kinetic energy of the system is equals to work done by all the forces. Okay, so in order to find out the final kinetic energy of the system, you have to assign the masses. Let the mass of earth be m, mass of the ball be small m. Okay, mass of the earth is m, mass of the ball is small m. What is final kinetic energy? Final kinetic energy of system is nothing but half, okay, m into v naught square, okay, plus half m into 0 square. Okay, what is initial kinetic energy of the system? Initial kinetic energy of the system is nothing but half. I'm drawing out the final kinetic energy and initial kinetic energy as seen by this observer. Okay, kinetic energy, work done, those are dependent upon frame of references. Okay, so what is the initial kinetic energy? Half m v naught square, m v naught square plus half m v naught square. Why? See, half m v naught square plus half mv naught square. That is the initial kinetic energy. Okay. What are the forces doing work out here? See, the only forces acting between these two bodies are mg out here and mg out here. Okay. See, if the earth pulls this body with gravity force mg downward, equal and opposite reaction force would be applied by the ball on the earth of same value mg. Okay. Now, because the earth is so massive, the mass of the earth is so means the earth is so massive, this amount of force, see, mg is a very minute amount of force, no, but mg is mass of this body into g. Okay, so because the mass of the earth is very large, okay, this force or this minuscule force or this small amount of force wouldn't be able to accelerate this earth by any amount or any significant amount. That's why the velocity out here is v naught, the velocity out here also would be v naught. The velocity of earth out here is zero, the velocity of earth when the ball collides is also zero. See, even if you apply this analogy, mg is downward out here, mg is upward out here, even that forces will act out here, no, mg is downward out here, mg is upward out here. Now, because of this mg force, the ball is accelerated down. But is the earth accelerated upward? Yes, by a very small amount. Okay, and that small amount is neglected in our kinematics calculation. So even if the earth is accelerated out here, that acceleration is neglected. Okay, so initial velocity is v naught, final velocity is also v naught. Initial velocity of the earth is zero, final velocity of the earth is also zero. Okay, so now my problem is, what is the work done? See, because the acceleration, see, out here, okay, from this frame of reference, when the ball collided with the earth, how much distance did the ball cover? The ball has covered h amount of distance, no? Okay, so the ball has covered h amount of distance, and it is it positive work or negative work? See, mg is acting downward, the displacement of the ball is also downward. What is actually happening is, see, v naught is acting upward, okay, and because of this mg force, okay, the ball is slowly being deaccelerated and this earth is catching up to the ball. Okay, so from this frame of reference, mg is acting downward and it happened over a displacement of h. So the work done is equals to mgh, mg which is the force and displacement which is the h, and it is positive. Why positive? Because the direction of force and the direction of displacement of the ball are same. Okay, now just apply kinetic energy, work energy theorem. Final kinetic energy, half mv naught square plus 0. Okay, this entire thing is 0 minus initial kinetic energy. Initial kinetic energy is nothing but half mv naught square plus half mv naught square is equals to mgh. Okay, this and this would get cancelled, or half mv naught square is equals to mgh, or v naught square is equals to 2gh, or v naught would be equals to under root of 2gh. So it doesn't matter which frame of reference you are observing. Okay, the work done by gravity force would be the same. Okay, this is the same formula. That means, see, even though kinetic energy and the work done, okay, are dependent upon frame of reference, the total energy expenditure of the system, okay, the energy expended by the system, okay, won't be dependent upon frame of reference. That is what the question is trying to tell us. Okay, work is nothing but, see, in your physics up till now, work is nothing but dot product of force and displacement. What the actual definition of work is, conversion of one form of energy to another. Okay, in your physics you mostly learn about mechanical energy. Okay, mechanical energy is divided into kinetic energy, potential energy. Okay, the real definition of work is conversion of one form of energy to another form of energy. That will learn better in thermodynamics. Okay, that is the true definition of work. In this question, I'll just briefly discuss the type of collision and the parameter for which what happens. Okay. See, there are basically three types of collision. Okay. Perfectly elastic, inelastic, and perfectly inelastic. In perfectly elastic collision, what happens? The ball bounces back after collision. Okay. In elastic, somewhere between, say, in elastic, we'll deal with something but called coefficient of restitution. For perfectly inelastic collision, okay, the bodies stick together after collision. Okay, this is an example of rubber ball. Okay, this is an example of chewing gum and wall. Okay, if you throw chewing gum to a wall, what happens? It sticks together, no? Okay, for all types of collision, you can always apply conservation of momentum. Okay, momentum before collision is equals to momentum after collision. Okay, momentum of the system before collision is equals to momentum of the system after collision. Understood? For perfectly elastic collision, you can apply conservation of kinetic energy. That means kinetic energy of the system before collision is equals to kinetic energy of the system after collision. Whereas for inelastic and perfectly inelastic collision, the kinetic energy of the system won't be conserved. Okay, some amount of energy from the system would be converted into heat or sound or any other matter. Okay, the coefficient of restitution for elastic is 1. Okay, the coefficient of restitution for inelastic is from 0 to 1. The coefficient of restitution for perfectly inelastic is 0. I'll give you a little bit more brief of what is coefficient of restitution. Okay, see, coefficient of restitution is nothing but relative velocity of separation divided by relative velocity of approach. Now, relative velocity of separation, when does separation occurs? After collision. So after collision, okay, what is relative velocity means? You have to take the frame of reference on any one of the body. Okay, suppose take the frame of reference on this body, okay, or this body, any body. Okay, that means what? This body would try to move away from this body with velocity v4 minus of v3 minus of v3. So velocity of separation is nothing but v4 minus v3. Okay, it doesn't happen to be in 1D. Okay, it can be in 2D. This velocity can be a 2D vector or a 3D vector. Okay, it does not necessarily have to be a 1D vector. It can be a 2D vector or 3D vector. The formula will remain the same. Now approach, when does approach happen? Before collision. Okay, now the main thing out here is, most of you get confused, is if you take the frame of reference, okay, on body 1, say this is body A, this is body B, this is body A, this is body B. Okay, if you take the frame of reference after collision on body A, you have to take the frame of reference before collision on body B, and vice versa. That means if you take the frame of reference after collision on B, that will take the frame of reference before collision on A. Okay, so what would be the velocity, what would be the observer on B seeing A approach itself with? Okay, the velocity of A as seen by observer B would be v1 minus v2. Okay, so the velocity of approach would be v1 minus v2. Okay, how did I see? This direction is positive, this direction is negative, this direction is positive, this direction is negative. While dealing with vector quantities, always assign the coordinate system. Okay, doesn't matter the type of vectors. Okay, doesn't matter the means direction of vectors or 1D, 2D or 3D vectors. The formula for coefficient of restitution will always be same. Okay, velocity of separation, okay, divided by velocity of approach. It doesn't matter which frame of reference you see it from, as long as the frame of reference before collision and frame of reference after collision are different, this formula will be correct. Okay, this much is known. And you already know coefficient of restitution for perfectly elastic is 1, for inelastic is 0 to 1, and for perfectly inelastic is 0. So in this question, what happens is a ball of 1 gram moves with velocity v1, which is given by 3I minus 2j, experience a perfectly elastic collision with another particle of mass 2 gram. Okay, with velocity v2. v2 is given as 4j minus 6k. Okay, find the velocity of the formed particle if the component of v1 and v2 are given in assignment. Okay, out here in the question, inelastic collision is given. That means what? The coefficient of restitution is 0, and in inelastic collision the bodies stick together after collision. Okay, the bodies will move together after collision. So say before collision it was this value, and after collision both the bodies sticks together and moves with some common velocity v. Okay, this is before collision, this is after collision. And in elastic collision what happens? The bodies stick together. In every type of collision, okay, what can you always apply? Conservation of momentum. So what is the momentum before collision? 1g into v1 plus 2g into v2 should be equals to 1g plus 2g is nothing but 3 gram into v. Okay, now substitute the vector. 1 into what is v1? v1 is nothing but 3i minus 2j plus 2 into 2 gram into what is v2? v2 is nothing but 4j minus 6k. Okay, is equals to 3 gram into, acha, let this velocity be xi, I don't know what is, plus yj plus zk. I don't know what are the values of xi and xy and z. Okay, so if we solve this one, what will happen? See, 3i minus 2j plus 8j, for 2 is 8 minus 12k. Okay, so 3i, there is no parameter of I, minus 2j and plus 8j will become plus 6j. So if I solve this, minus 2j and plus 8j, it will become plus 6j. Okay, minus 12k. I'm just writing this minus 12k out here. Okay, minus 12k is equals to 3 into xi plus yj plus zk. Okay, now if you divide these three out here, what will happen? Divided by 3. Okay, these three I'm dividing out here. It would be I plus 2j minus 4k. It would be xi plus yj plus zk. That means what? The x component of velocity is 1, the y component of velocity is 2, the z component of velocity is minus 4. If I want to find out the magnitude of this velocity, how do I find out the magnitude? Magnitude is nothing but under root of 1 square plus 2 square plus minus 4 square, which is 4 square, which is equals to, or magnitude of velocity, okay, which is equals to 1 plus 4 plus 16 is equals to under root of 21. Okay, meter per second. So the question is simple enough. So out here inelastic collision is happening. Okay, so the question is asking, there are two bodies out here. Okay, m1 moving with velocity v1 and m2 moving with velocity v2. Perfectly inelastic collision, okay, is happening. Okay, m1, this is m1 and m2 sticks together. In perfectly elastic collision, what happens? Both the bodies stick together, no, and both moves with same velocity v. Okay, now the question is asking, find the increment in kinetic energy. The question is phrased little bit differently. Find the decrease in kinetic energy. Okay, see, always remember, in perfectly elastic collision, the kinetic energy of the system remains conserved. Okay, neither increases nor decreases. In inelastic collision, that means when the coefficient of restriction is between 1 and 0, the kinetic energy of the system reduces by a little bit. Okay, and where did that energy go? It got converted into either heat or the sound. See, if you collide two objects, you hear a sound, no? Okay, that is coming from the kinetic energy of the two bodies. Okay, and in inelastic collision, when the bodies stick together, okay, maximum amount of kinetic energy loss takes place from the system. That means the system loses maximum amount of kinetic energy. Okay, so the total kinetic energy out here would be much bigger than the total kinetic energy out here. Okay, so what is the decrease in kinetic energy? Decrease in kinetic energy is nothing but final kinetic energy, or half. What is final kinetic energy? Half m1 plus m2 total mass of the system into v. This is the final kinetic energy. Okay, minus what is the initial kinetic energy of the system? Half m1 v1 square plus half m2 v2 square. Okay, now there's a problem out here. Okay, I have to find v in terms of v1 and v2, and in every type of collision what can I apply? Conservation of momentum. See, whenever you hear collision, okay, there are only two formulas you can apply: conservation of momentum, and one of them is coefficient of restitution, and the third one is, if you check for perfectly elastic collision, you can apply a third formula called conservation of kinetic energy. Okay, so in any type of collision you can always apply conservation of momentum. So initial momentum before collision, okay, is nothing but m1 v1 plus m2 v2. What is the final momentum of collision? What is the final momentum of the system after collision? m1 plus m2 into v. So from this equation I'll get v is equals to m1 v1 plus m2 v2 divided by m1 plus m2, isn't it? Now see, in this equation what I have to find out in the answer is this value or this parameter, but in this equation I have to substitute the v from out here to out here. Okay, the v will be substituted from out here to out here. Okay, and when you do that you'll get equation something like, what I simply did out here is I substitute the velocity v out here. See, this equation and this equation are the same thing, except this value of velocity v is substituted by this parameter. See, this entire thing is nothing but the v out here. Okay, now what can I do? See, this whole square can be written down as this square. Okay, if I just modify this one, this can be this square divided by whole square, isn't it? Now this m1 plus m2 and this square would get cancelled. Okay, so I'm cancelling out this one. Okay, so our main parameter would be half this value. Okay, now just make it little bit neat and clean. I'll just draw the half out. Now what can I do? I can open up the bracket. If I open up the bracket, this positive will become negative. Okay, and it would become somewhat like this. Now see, there's a certain thing I can do. Okay, I can take m1 half common from all the terms, and from the remaining term I can take m1 and m2 as LCM. What I've done out here is I've taken half common and written down the rest of the term. Now if I take LCM out here, okay, if I take m1 plus m2 as LCM, okay, then what do I have to do? I have to multiply m1 plus m2 with this term and this term. So what I'll get is, now what I have done out here is I have taken m1 plus m2 as LCM and multiplied m1 plus m2 with this term. It would become, one of the term would become m1 square v1 square, and the other term would become m2 m1 into v1 square. Similarly, one of the term would become m1 m2 v2 square, and the other term would be m2 square v2 square. Okay, I've just taken LCM and multiplied this term with this. Now what can I do is I can expand this term. A plus b whole square is nothing but a square plus b square plus 2ab. Okay, so just let me expand this term. Okay, a plus b whole square. So if I expand this entire term, what will happen? We'll get a square plus b square plus 2ab. Now check out here. m1 square v1 square and minus m1 square v1 square would get cancelled. So this term and this term would get cancelled. m2 square v2 square and minus m2 square v2 square would get cancelled. So let me just erase these terms. Okay, So you're left with these three terms: m1 m2 v1 v2 minus m1 m2 v1 square minus m2 m1 m2 v2 square. Okay, if I take m1 m2 common from the numerator, okay, what will happen? m1 m2, okay, I can take. So if I take m1 m2 common, I'll get v1 v2 minus v1 square minus v2 square. Okay, so let me write this all close together: v1 v2 v1 v2 minus v1 square minus v2 square. Okay, so these are the terms. Okay, now everything is sorted out. See, if I take minus common out here, okay, if I take minus common out here, that means I'm taking minus common from this term. Okay, it will be nothing but v1 square plus v2 square minus v1 v2. So if I take minus common, this would become plus, this would become plus, and this would become minus. I'm taking minus from common from this term. Okay, okay. And what is v1 square plus v2 square minus v1 v2? It is v1 minus v2 whole square. A minus b whole square is nothing but a1 square plus a minus b whole square is nothing but a square plus b square minus 2ab. Okay, a minus b whole square is nothing but a square plus b square minus 2ab. Okay, I have made a little bit of error out here. Out here it would be minus 2 v1 v2. Okay, minus 2 v1 v2. Why? See out here. When I expand this term, the mistake I made was writing m1 m2 v1 v2. It would be 2 m1 m2 v1 v2 because a plus b whole square is nothing but a square plus b square plus 2ab, no? So that 2 I have forgotten to write out here. Now if we contract this one, what will become? v1 minus v2 whole square or v2 minus v1 whole square. Both will have the same effect. Okay, so v1 minus v2 whole square. Okay, now if I take this entire thing common, okay, decrease in kinetic energy is nothing but I'm taking this m common, m1 m2 common or outside the bracket. Okay, I'm even taking this m1 plus m2 outside the bracket divided by m1 plus m2. So I'm taking this common. Okay, the bracket should be erased. Okay, and this bracket has no sense right now. Okay, let me write v1 minus v2 whole square properly. v1 minus v2 whole square. Or if I rearrange this, if I take this minus outside, okay, minus half m1 m2 divided by m1 plus m2 into v1 minus v2 whole square. Okay, what does the minus signify? The minus signifies that, see, I have taken out here is final kinetic energy minus initial kinetic energy minus initial kinetic energy. What the minus signifies is that the energy, okay, is decreased. That means final kinetic energy is lesser than the initial kinetic energy. That is why that negative sign is out. Understood? In this question, what is happening is there is a mass m1. Okay, it is traveling with some velocity v, and there is a stationary mass m2. Okay, now these two masses collided elastically. Okay, so the question is asking, find out the fraction of energy loss of the colliding particle. That means find out the energy loss of this particle after collision. Okay, see, whenever problems are based on collision, there are one of four equations that you can apply. The first equation is conservation of momentum, that is valid for every type of collision. Okay, the second one is conservation of kinetic energy, that is valid only for elastic collision. Okay, and the third equation you can make is coefficient of restitution, but coefficient of restitution is nothing but velocity of separation divided by velocity of approach. So out here they are colliding elastically. So the entire kinetic energy of the system will remain conserved. What will change? The kinetic energy of the colliding particle. Why? Because after collision, some amount of kinetic energy from this particle will be transferred onto this particle. So after collision, now the question is asking, after elastically colliding, if the particle bounces at right angle to its original motion of direction. That means I'll solve with case number 1. Okay, this is before collision, this is after collision. After collision, what is happening? M1, okay, jumps off with V1 in perpendicular direction. That means it came in this direction, jumped off in this direction. And M2 will have some velocity, let's say V2, making an angle theta with the horizontal. I neither know about V2, neither know about theta. Okay. My main point out here is, what is the question asking? The question is asking change in kinetic energy or fractional change in kinetic energy. Okay. So loss in kinetic energy is what? Loss in kinetic energy. Loss in kinetic energy is nothing but initial kinetic energy minus final kinetic energy of M1, isn't it? Loss in kinetic energy of mass M1. That is what the question is asking. Okay. Striking particle. That means striking particle is M1. Okay. So loss of kinetic energy is nothing but half M1 U square. Initial kinetic energy minus final kinetic energy V1 square. Okay. Some of you might have the confusion, so it should be final minus initial. Okay. Final kinetic energy of M1 is much lesser than initial kinetic energy. So this would have a negative value, no? To compensate for that negative value, I have already written loss of kinetic energy out here, isn't it? So loss in kinetic energy is nothing but initial kinetic energy minus final kinetic energy. Okay. Okay. Percent loss in kinetic energy. How do you write percent loss in kinetic energy? This is the loss in kinetic energy. Loss in kinetic energy is nothing but half m1 u square minus half m1 v1 square divided by percent loss means loss in kinetic energy divided by the total initial energy. What was the initial energy? Half m1 u square. Half m1 u square. So our question is asking into 100. Okay. But out here they haven't asked us about percent, they have asked us about fraction. This is fraction. Fraction means you do not have to multiply by 100. Okay. So I have to find out this parameter. Okay. This parameter is the thing that I have to find out. So let's simplify my parameters. Okay. Can I cancel half m1 from numerator and denominator? So I'll get something around u square minus v1 square by u square. Okay. And if I further rectify it, it would be 1 minus v1 square by u square. So this is the parameter that I have to find out in the both the cases. This is the fraction loss in kinetic energy. Now see. So how do I get v1 square by u square? Okay. Can I apply conservation of momentum? So applying conservation of momentum. Applying conservation of momentum. What do I get? What is the initial momentum? Let this direction be I cap. Okay. Let this direction be x-axis and the upward direction be y-axis. So before collision, what is the total momentum of the system? M1 U I cap, M1 U I cap plus M2 into 0. Is there any J component of velocity? No. So total initial momentum of the system was M1 U I cap. What is the total final momentum of the system? M1 V1 J cap. Okay. M1 V1 J cap plus M2 also has some velocity, no? Plus m2 v2 cos theta I cap, the component of this momentum along x-axis, minus m2 v2 sin theta j cap, isn't it? The component of this momentum along this axis. Okay, so let me adjoin this value and this value together because both are j cap, no? So m1 u I cap is equals to m1 v1 minus m2 v2 sin theta j cap plus m2 v2 cos theta I cap. Okay, what I actually did out here is I compiled these two j values together. Okay, now from this conservation of momentum equation, I can create two values or two further equations. See, the first equation should be, okay, the first equation. See, the in the x component, that means in the I values, okay, the x component of momentum before collision and after collision should be same, isn't it? So x component, that means I cap component, okay, the x component of momentum before collision is m1 u1, which should be equals to the x component of momentum after collision, which should be m2 v2 cos theta, m2 v2 cos theta. Similarly, from the same equation for y component, or j cap component, okay, the initial y component of momentum, which is equals to 0, there is no value of j, no? Okay, so initial y component of momentum is equals to final y component of momentum. What is the final y component of momentum? m1 v1, this value, isn't it? m1 v1 minus m2 v2 sin theta. Okay, okay, now these are the two equations I obtained. Okay, now from these two equations, somehow a trigonometric function is obtained out here. So how do I disappear this trigonometric function? Simply just make it square. Okay, somehow if I square this one, if I obtain a value of cos square theta and sin square theta, and somehow if I can add cos square theta plus sin square theta, cos square theta plus sin square theta is 1, no? So if I square this, I get the intuition that if I square this both equation and add them, somehow this trigonometric term will disappear. Okay, see, there are basically two equations I obtained. Okay, this was the x component and this was the y component. So simply if I take this minus m2 v2 sin theta to the left hand side, it will become equals to, no? So this would become m1 v1 equals to m2 v2 sin theta. What I've simply done is I've taken this minus to the opposite hand side. Okay, now can I square these both terms? Squaring left hand side and right hand side of equation 1, okay, will give us m1 square u1 square is equals to m2 square v2 square cos square theta. Similarly, squaring left hand side and right hand side, okay, will give us m1 square v1 square is equals to m2 square v2 square sin square theta. Okay, and why did I square this left hand side and right hand side? If I add these two equations, okay, if I add this x component of equation and y component of equation, what do I get? m1 square u1 square plus m1 square, not u1 square, u square. This should be u. This should be u. The x component of velocity is u. Okay, m1 square u square. Okay, u out here should be u plus m1 square v1 square should be equals to m2 square v2 square cos square theta plus m2 square v2 square sin square theta. Okay, now from the right hand side, can I take m2 square v2 square common? Okay, so out here m1 square, I'm taking m1 square common from the left hand side, so m1 square into u square plus v1 square should be equals to m2 square v2 square sine square theta plus cos square theta, sine square theta plus cos square theta. This should be equals to 1 because we know that sine square theta plus cos square theta is equals to 1. So our entire equation from conservation of momentum comes out to be this value. Okay, this value, or m1 square. Acha, what do I need to find out? I need to find out the ratio of v1 square by u square, no? So let me simplify out here only. Okay, dividing the left hand side by v1, sorry, u square, okay, and right hand side by u square. What I'm trying to do is I'm trying to obtain a parameter in this form. Okay, so it is easier for us. U square, it would be m1 square into 1 plus v1 square u square. Okay, this is equals to m2 square v2 square by u square. So this is the first step of equation that I get from conservation of momentum. Achha. What else equation can we apply out here? Now what can I do is I can deduce another equation from conservation of kinetic energy. Okay, so what was the initial kinetic energy? Half m1 u square. Did this body have any kinetic energy? No. Okay, so kinetic energy before collision is half m1 u square. What is the final kinetic energy? The final kinetic energy is half m1 v1 square plus half m2 v2 square. So the final kinetic energy after collision is half m1 v1 square, m1 v1 square plus half m2 v2 square. Okay, whenever there is collision, there are basically four equations. Conservation of momentum, that is valid everywhere. Conservation of kinetic energy, only for elastic collision. Okay, and the third equation comes from coefficient of restitution, or equation of coefficient of restitution, which is basically velocity of separation divided by velocity of approach. Okay, so out here I'm cutting out the half, or I can get, my equation becomes m1 u square is equals to m1 v1 square plus m2 v2 square. And what is the parameter that I have to obtain? v1 square by u square. So I divide the entire left hand term by u square and right hand term by u square. So what do I get? m1 is equals to m1 v1 square by u square plus m2 v2 square by u square. Now I have to find out this term, no? 1 minus v1 square by u square. Okay, and in this term there is no use of v2. So somehow in these two equations, this is the equation I obtained from conservation of kinetic energy, and this was the equation I obtained from conservation of momentum. So between these two equations, somehow using these two equations, I have to make this component of v2 square disappear. And how do I do that? See, if I just multiply any of the term, see, by mass, okay, I can either, see, let me rectify this equation, okay, or m1 minus m1 v1 square by u square is equals to m2 into v2 square by u square. Okay, so if I take m1 common out here, okay, it will be 1 minus u v1 square by u square. So I'm taking m1 common out here, 1 minus v1 square by u square. Now if I take this m2 out here, what will happen? Divided by m2. Okay, This is the modified form of this equation, and I'm writing this v2 square by u square closer to the equals to v2 square by u square. Okay. Similarly out here, if I take this m2 down out here, what it would become? m2 square, isn't it? Okay. And I can write this v2 square by u square closer to equals to, or v2 square by u square. Simple enough. Now see, from both this equation, I do not need this term, no? So can I equate v2 square by u square is equals to v2 square by u square? So this entire term would be equals to this entire term. So m1 by m2 1 minus v1 square by u square should be equals to m1 square by m2 square 1 plus v1 square by u square. So if I equate from these two terms, see, if I equate v2 square by u square from this equation and this equation, what do I get? I get around, from the first equation, m1 by m2 is equals to 1 minus v1 square by u square from this equation, and from this equation the same value is nothing but m1 square by m2 square into 1 plus v1 square by u square. Okay, fair and fine. Now what do I do? I can cancel out the m1 and square out here, m2 and square out here. Okay, what I just did out here is I equated v2 square by u square from this equation and v2 square by u square from this equation. I equated both these values together. Okay, and I got something like this, and from this combination I have to take out this value. Okay, so out here, see one more thing. Okay, out here I do have v1 square by u square directly. Okay, I can directly write this fractional loss in kinetic energy is equals to this value, but out here I'm facing a problem. What? Because this value already has a variable of mass and also has a variable of velocity, no? So somehow I either need to convert all my variables in terms of mass or all my variables in terms of velocity. Okay, I'm unhappy with the equation containing both types of variable. Understood this one? So how do I do this? I'll simply copy this equation to the next page. Okay, so out here, for the ease of calculation, what I do out here is I take v1 square by u square to be x. So let x is equals to v1 square by u square for the ease of calculation. So I have to find out 1 minus x. So out here I can modify this equation as 1 minus x square. Okay, I have to find out 1 minus x square is equals to m1 by m2 into 1 plus x square. Okay, if I cross multiply, m2 minus m2 x square is equals to m1 plus m1 x square. Now let's isolate the value of x, or m2 minus m1 is equals to m2 x square plus m1 x square, or x square is equals to m2 minus m1 divided by m2 plus m1. This is the value of x square, isn't it? And 1 minus x square is nothing but 1 minus of m2 minus m1 divided by m2 plus m1, or it would be m2 plus m1 minus of m2 minus of m1 plus of m1. Okay, divided by m2 plus m1. So out here m2 and m2 gets cancelled, or 2 m1 by m2 plus m1. So this is the fractional loss in kinetic energy of the first particle, m2 plus m1. Okay, now for the second part of the problem, it has the same problem statement where a mass m1, which was initially moving with you, okay, collides with another stationary mass which was at rest. So after collision, what will happen? After collision, all these masses, okay, m1 will move with velocity v1, and m2 with move with velocity v2. But unlike the previous problem, okay, where the mass m1 is bouncing off at right angle, all these v1, v2, and u will lie on the same line. Okay, that means if you use only one vector of x-axis, our problem can be solved. So I can similarly apply conservation of momentum, no? Okay, but instead of using I cap and j cap, I'll write everything for I cap. Okay, because there is no component of j cap before or after collision, isn't it? So if I write the component of I cap, so what is the momentum before collision? m1u. Okay, total momentum of the system before collision is m1u plus m2 into 0, which is equals to 0. What is the momentum after collision? m1 v1 plus m2 v2. And what do you have to find out? Fraction of kinetic energy lost. If I calculate, it is nothing but final kinetic energy of m1, sorry, initial kinetic energy of m1 minus final kinetic of energy of m1 divided by total kinetic energy of m1, total initial kinetic energy of m1, which would come as 1 by v1 square by u square. So I have to find out the same thing basically, okay, but with little bit different sets of equation or easier sets of equation. Okay, now I can apply conservation of kinetic energy out here, but you know what would be much simpler? Using coefficient of restitution. Okay, whenever there is collision, you can use three equations. One is conservation of momentum, you can use for all types of collision. Second one is conservation of kinetic energy, that can be only used for elastic collision. And the third one is coefficient of restitution. For coefficient of restitution for elastic collision, okay, coefficient of restitution for elastic collision is 1. What is coefficient of restitution? Velocity of separation. Okay, what is velocity of separation? v1 minus v2, v1 minus v2. Okay, and what divided by velocity of approach? What is velocity of approach? Okay, velocity of approach is minus u. Why minus u? Because this person or an observer out here will see the block m2 move towards itself with minus u. Okay, it doesn't matter where you keep. For coefficient of restitution, whenever you are using velocity of separation divided by velocity of approach, okay, if you are putting the observer for velocity of separation out here, put the observer for velocity of approach on the different body. That means the observer for velocity and separation and the observer for velocity of approach should be on different bodies. Okay, and you can also write this as, or 1 is equals to, you can multiply the numerator by minus 1, v2 minus v1 divided by u, which happens the same thing when you put the velocity of approach for approach out here, observer out here, and velocity of separation, the observer out here. See, you put the observer for separation out here and observer for approach out here, you'll get this equation. Or u is equals to, or from this equation I'll get u is equals to v2 minus v1, isn't it? Okay, what do I need to find out? I need to find out v1 square by u square. Okay, so how do I find it out? Okay, if I put u, if I put divide this entire equation by u, I'd get around 1 is equals to v2 by u minus v1 by u. Similarly, if I divide this entire equation by u, by u, by u, okay, I can get m1 is equals to m1 v1 by u plus m2 v2 by u. Okay, now there are two equations, two variables, and what do I need to find out? v1 square by u. To make this simple, okay, in order to avoid clutter with these variables, lot of variables, I'll just make, see, I need to find out v1 square by u square, no? So if I consider, let v1 by u be x and v2 by u be y, what will happen is these equations will be much simpler. Okay, so I can rewrite this equation as m1 is equals to, c, our physics ended out here. After writing these two equation, our physics already ended. Okay, now we are just playing with equation. What do I need to find out? This. And how do I need to find out from these two equations? Okay, see, tougher problems in physics are nothing but a conceptual approach plus a handful of equation. Okay, so whenever you are revising irodov, no, for JEE advanced, this kind of problems are more or less kind of this kind of approach you should keep for JEE advanced. So whenever you're facing a tough problem, okay, you must take the approach, okay, and then practice a lot of equation. Okay, the approach will be more or less same for every type of question. What will differ is the type of equation. Okay, so you do not need to memorize what is substituted out here, what is means cancelled out here. That will get different from equation to equation, from question to question, and it will be different for different questions. Okay, and that can only be perfect, not perfected, taken in grabs by a lot of practice. Okay, there is no one in the world that can teach you or spoon feed you how to do equations. That you can only do yourself by a lot of practice. Okay, the main focus out here should be the approaches or the intuition. How do I get the equations? Okay, I must do this one. I must build up this two equation, and from this two equation I can clearly find out this one. Not only for this question, for the entire subject of physics. Okay, whenever there is difficult questions, this is the simple kind of approach. Okay, the approach should be the physics part, the playing with equations should be the not mathematical part, it should be from your end of practice kind of thing. Okay, so out here m1 into v1 by u is x plus m2 into v2 by u is y. Out here 1 is equals to this, 1 is equals to v2 by u. v2 by u is y minus v1 by u is x. So simple enough. So from this equation, can I get y is equals to x plus 1? See, if I send the x to the left hand side. Now can I substitute this y out here? Obviously I can. Or m1 is equals to m1x plus m2y. Okay, and y has to be substituted by x plus 1, isn't it? So y has to be substituted by x plus 1. Okay, so in this equation I need to find out the value of x, and after finding out the value of x, what I must find out? I must find out the value of 1 minus x square, which is the fraction of kinetic energy lost. Understood? So let's copy these two equations out here. Let's copy this equation on the next page and let's solve it out. The equation solving should be much easier part. Okay, so I'm just copying this equation out here. m1 is equals to m1x plus m2 into x plus 1. This is the equation. Let's just solve this equation for x. Okay, I'll just solve this equation for x. What I did out here is I opened up the bracket. Now what I did out here is I have taken this m2 to the left hand side. So m1 minus m2 and m1 plus x plus m2x is kept out here. What I'll take out here is I'll take the x common out here. Now if I take x common out here, it would be m1 plus m2, and I can find out x is equals to m1 minus m2 divided by m1 plus m2 if I divide this entire m1 plus m2. Understood? And now what must I do? I must find out 1 minus x square. Okay, so what is the value of x? This one. What is the value of x square? This entire square. And what is the value of 1 minus x square? Or the value of 1 minus x square is nothing but 1 minus m1 minus m2 by m1 plus m2 whole square, isn't it? Or which should be equals to, acha, can I separate out the bracket? Separate out the bracket means make it like this. Okay, m1 square divided by m2 square. Okay, now can I take LCM? Obviously I can take LCM. m1 plus m2 whole square into m1 plus m2 whole square minus of m1 minus m2 whole square. Okay, now when you open up these brackets, a plus b whole square and a minus b whole square, a square plus b square plus 2ab, and a square minus b square, a minus b whole square is nothing but a square plus b square minus 2ab. So if you add, see, this a square or m1 square and this minus m1 square would get cancelled, plus m2 square and minus m2 square would get cancelled. Out here 2 m1 m2 and out here minus 2 m1 m2. That minus 2 m1 m2 would be multiplied by this minus and it would become plus 2 m1 m2. So 2 m1 m2 out here and 2 m1 m2 out here would be 4 m1 m2. 4 m1 m2 divided by m1 plus m2 whole square. If you are still confused out here, just open this bracket by a plus b whole square using the formula of a plus b whole square and open this bracket using the formula of a minus b whole square. Okay, you get this answer. So this is the fraction of kinetic energy lost in part 2. Okay.